Good evening, ladies and gentlemen. How is everyone doing? Why stressed and not well? The moon assignment is not that difficult, but I told you guys not to underestimate the assignment. So tomorrow we're writing our physics semester test. Good luck with that one. So, in last night's lecture, we ended off with our lecture on all the terrestrial worlds. We've learned about Mercury, Venus, Earth, Saturn, Earth, Earth's moon, the moons of Mars. But now we're going to start looking at the Jovian worlds, meaning Jupiter, Saturn, Uranus, Neptune, as well as their moons. So the aim of this chapter is the four Jovian worlds that forms part of the outer solar system, and after that, the only thing we have left is the asteroid belt and the Oort cloud. So who of you have seen Jupiter through a telescope? So this is one of my favorite objects I usually like to observe. And you can usually see a couple of its moons as well. And can you guys tell me what this feature on Jupiter is? It's a giant storm. So it's the red storm or the red eye of Jupiter. And it's about the size of 4 Earths. And have you guys seen Saturn through a telescope? Goodness, I've load shedding at 6, but we'll watch recording. That's no problem. So Saturn is also a very beautiful object to observe, and depending on where we are in our orbit towards around the sun and towards Saturn, but it is very beautiful if we can see the entire ring. And then Uranus. So Uranus also has rings. So Uranus and Neptune are the 2 planets we cannot see with our naked eye, because then we are reaching the limits of -6, -7 apparent visual magnitude. And then there is Neptune. So what do these planets have in common? So what will you guys tell me about these planets? Cold and big, so they're not that cold. So all gas planets, yes. And they're all very big, much larger than Earth. And then lastly, I just added this for tradition's sake, but this is an image of Pluto. That's no longer a planet. In the last 3 chapters, you watched our solar system form, then studied Earth and other terrestrial planets, as they have evolved to the present day. In this chapter, the Jovian, so the Jupiter-like planets, will be a challenge to your imagination. They are such alien worlds. They would be unbelievable if you didn't have direct observational evidence to tell you what they are like. In contrast, Pluto and other bodies in the Kuiper Belt are not planets, intriguing remnants of the planet construction process. You think you missed a planet. So there's no evidence for Planet 9, Mr. Melville. So as you explore, you will find answers to 4 important questions. So firstly, what are the properties of the Jovian planets? Secondly, what is the evidence that some moons in the outer solar system have been geologically active? Number 3, how are planetary rings formed and maintained? And lastly, what do Pluto and the other Kuiper Belt objects tell us about the formation of the solar system? The sulfuric acid clouds of Venus may seem totally alien to you. But compared with the planets of the other solar system, Venus is almost like home. For example, the 4 Jovian planets has no solid surfaces. The worlds of the outer solar system can be studied from Earth, but much of what astronomers know has been radioed back to Earth from space probes. The Pioneer and Voyager missions flew past the outer planets in the 1970s and 1980s. Galileo orbited Jupiter in the late 1990s, and the Cassini orbiter and probe arrived at Saturn in 2004. The New Horizons craft flew past Pluto in 2015 and is now sailing deeper into the Kuiper Belt. Juno arrived in orbit around Jupiter in 2016 for planned multi-year close-up investigation of the planet's magnetosphere and gravity field. Throughout this discussion, you will find images and data returned by these robotic explorers. The outermost planets in our solar system are Jupiter, Saturn, Uranus, and Neptune, the Jovian planets, meaning they resemble Jupiter. In fact, they are each individuals with separate personalities. Figure 18.1 compares the 4 outer worlds to each other and to Earth. One striking feature is their size. Jupiter is the largest of the Jovian worlds, over 11 times the diameter of Earth. Saturn is slightly smaller, and Uranus and Neptune are quite a bit smaller than Jupiter and Saturn, but still 4 times the size of Earth. Pluto, not pictured in this figure, is smaller than Earth's moon, but was considered a planet from the time of its discovery in 1930 until 2006, when it was reclassified as a dwarf planet. You will learn about Pluto's characteristics and the reason for that decision in this chapter. So here we can see a shadow of one of Jupiter's many moons on a planet. We can actually see that quite regularly. So Earth is a terrestrial world compared to these planets. So Jupiter, more than 11 times Earth's diameter, is the largest planet in our solar system. So here we can see the cloud belts and zones on Saturn are less distinct than on those on Jupiter. So these belts we can see with the telescope on Jupiter. It's actually beautiful to watch. Uranus and Neptune are green and blue colored because of small amounts of methane in the hydrogen-rich atmospheres. And then Uranus and Neptune are both about 4 times Earth's diameter. The other feature you will notice immediately when you look at figure 18.1 is Saturn's rings. They are bright and beautiful and composed of billions of ice particles. Jupiter, Uranus, and Neptune also have rings, but they are not easily detected from Earth and are not visible in the figure. Nevertheless, as you visit these worlds, you will be able to compare and contrast those 4 sets of planetary rings. The four Jovian worlds have hydrogen-rich atmospheres filled with clouds. On Jupiter and Saturn, you can see that the clouds form stripes and bands that circle each planet, known as belt zone circulation. You will find traces of these same types of features on Uranus and Neptune, but they are less distinct. Models based on observations indicate that the atmospheres of the Jovian planets are not very deep. For example, Jupiter's atmosphere makes up only about 1% of its radius. Below the atmospheres, Jupiter and Saturn are mostly liquid, so the conventional term for these planets, gas giant, should probably be changed to liquid giants. Uranus and Neptune are sometimes called ice giants because they contain abundant water in solid forms. Only near the centers do the Jovian planets have cores of dense material with the composition of rock and metal. None of the Jovian worlds has a definite solid surface on which you can walk. You can't really land your spaceship on the Jovian worlds, but you might be able to land on one of their moons. All the Jovian worlds have extensive satellite systems. Those moons are classified into two groups. One, the regular satellites, which tend to be large and orbit relatively close to their parent planet, with low inclinations to the planet's equator, moving in the prograde direction along with most objects in the solar system, versus, secondly, the irregular satellites, which tend to be smaller than the regular satellites, sometimes have retrograde and or highly inclined orbits, and are generally far from their parent planet. Astronomers have evidence that the regular satellites form approximately where they are now, as the planets formed, but the irregular satellites are mostly, if not all, captured objects. So what percent of the Jovian planet's radius is liquid? I'm not too sure about that. Some of the Jovian moons are geologically active now, while others show signs of past activity. Of course, geologically active activity depends on heat flow from the interior, so you might ponder what could be heating the insides of these small objects. You'll get some answers to that question later in this chapter. Jupiter is the largest and most massive of the Jovian planets, containing 71% of all the planetary matter in the solar system. Just as you used Earth, the largest of the terrestrial planets, as the basis for comparison with the others, you can examine Jupiter in detail as a standard in your comparative study of the other Jovian planets. Although Jupiter is very large, it is only 1.3 times denser than water. For comparison, Earth is more than 5.5 times denser than water. As you have already learned, the density of a planet is an important clue about the average composition of the planet's interior. Jupiter's shape also gives information about its interior. Jupiter and other Jovian planets are all slightly flattened. A world with a large rocky core, a mantle, would not be flattened much by rotation, but an all-liquid planet would flatten significantly. This Jupiter's oblateness, so the fraction by which its equatorial diameter exceeds its polar diameter, combined with its average density, helps astronomers calculate what its insides are like. Models show that the interior of Jupiter is mostly liquid hydrogen. However, if you jump into Jupiter carrying a kayak expecting an ocean, you would be disappointed. The base of the atmosphere is so hot and the pressure is so high that there is no sudden boundary between liquid and gas. As you fell deeper and deeper through the atmosphere, you would find the gas density increasing around you until you were sinking through a liquid. But you would never splash into a distinct liquid surface. Under very high pressure, liquid hydrogen becomes liquid metallic hydrogen, a material that is a very good conductor of electricity. Model calculations indicate that most of Jupiter's interior is composed of this material. That large mass of conducting liquid, stirred by convection currents and spun by the planet's rapid rotation, drives the dynamo effect and generates a powerful magnetic field. Jupiter's field is over 10 times stronger than Earth's field. A planet's magnetic field deflects the solar wind and dominates a volume of space around the planet called the magnetosphere. Jupiter's magnetosphere is 100 times larger than Earth's. If you could see it in the sky, it would be more than 5 times larger than a full moon, just as the case of Earth. Interactions between Jupiter's magnetic field and the solar wind generate powerful electric currents that flow around the planet's magnetic poles. These are visible at ultraviolet wavelengths as rings of aurora lights that are larger in diameter than Earth. In image A, we can see Jupiter's large conducting core and rapid rotation creates a powerful magnetic field that holds back the solar wind and dominates the magnetosphere. Colored blue in the diagram. High-energy particles trapped in the magnetic field from giant radiation belts. Then in image B. Aurorae on Jupiter are confined to rings around the north magnetic pole and the south magnetic pole, as shown in these ultraviolet images. Earth's aurorae follow the same pattern. The small shaped spots are caused by powerful electrical currents flowing from Jupiter's moon Io. The strong magnetic field around Jupiter traps charged particles from the solar wind in radiation belts a billion times more intense than the Van Allen belts that surround Earth. The spacecraft that have flown through these regions received over 4,000 times the radiation that would have been lethal for a human. At Jupiter's center, a so-called rocky core contains heavier elements such as iron, nickel, silicon, and so on. With a temperature 4 times hotter than the surface of the Sun and a pressure of 50 million times Earth's sea level atmospheric pressure, this material is unlike any rock on Earth. The term rocky core refers to the chemical composition, not to the mechanical properties of the material. Careful measurements of the heat flowing out of Jupiter reveal that it emits about twice as much energy as it absorbs from the Sun. This energy appears to be heat left over from the formation of the planet. In chapter 15, you saw that Jupiter should have grown very hot when it formed, and some of that heat remains inside, slowly leaking into space. So look back to figure 5.17b, the infrared image of Jupiter acquired by the SOFIA Airborne Telescope, shows a white stripe where the planet's internal heat flow is prominent. In 2016, the Juno probe began orbiting Jupiter on a path coming within 4,200 kilometers of the cloud tops, making detailed measurements of the planet's magnetosphere and gravity field for insight into its internal structure. There's a common misconception that Jupiter is a ball of gas. In fact, as you have learned, Jupiter is almost entirely a liquid planet. Its atmosphere is only a thin outer skin of turbulent gases and clouds. The processes you will find there are repeated in slightly different ways on the other Jovian worlds. So notice 4 important ideas. Firstly, the atmosphere is hydrogen-rich and the clouds are confined to a shallow layer. Secondly, the cloud layers are located at certain temperatures within the atmosphere where ammonia, ammonium hydrosulfide, and water respectively can condense. 3. The belt zone circulation pattern of colored cloud bands circling the planet like stripes on Charles' ball is related to the high and low pressure areas found in Earth's atmosphere. Then number 4, the large circular or oval spots seen in Jupiter's clouds are circulating storms that can remain stable for decades or even centuries. Photos of Jupiter lead to the common misconception that the clouds are at the top of the atmosphere. Realize that the atmosphere of transparent hydrogen and helium extends high above the cloud tops. What you see in the photos is only the cloud layers. Jupiter has 4 large moons and at least 60 smaller ones. So this is outdated. So this textbook is a couple of years old. The latest stats or figures I've seen is Jupiter has about 84 moons currently that has been classified. So larger telescopes and modern techniques are continuously finding more small moons orbiting the Jovian planets. And each of the Jovian planets probably has many more small undiscovered moons. Some of the small moons are probably captured asteroids. In contrast, the 4 largest moons of Jupiter, called the Galilean moons after the discoverer Galileo, are clearly related to each other and almost certainly formed with Jupiter. So here we can see from left to right, the moons are Io, Europa, Ganymede, and Callisto. So note that Io is almost exactly the same size as Earth's moon. So what can you tell interesting, what facts do you know about these moons? Is everyone still awake? So Europa is very interesting object because we can detect water on Io that might have bacterial life. So that is something interesting to visit in the future. The outermost Galilean moons, Ganymede and Callisto, are about the size of Mercury, 1.5 times the size of Earth's moon. In fact, Ganymede is the largest moon in the solar system. Ganymede and Callisto have low densities of only 1.9 and 1.8 grams per cubic centimeter, respectively, meaning they must consist roughly of half rock and half ice. Observations of the gravitational fields by the Galileo spacecraft reveal that Ganymede has a rocky or metallic core and lower density icy exterior. So it is differentiated. Callisto is apparently only partly differentiated. Both moons interact with Jupiter's magnetic field in ways that show they probably have mineral-rich layers of liquid water 100 kilometers or more below their icy crusts. Callisto's surface and most of Ganymede's surface appear old because they are heavily cratered and very dark. The continuous blast of meteorites evaporates surface ice, leaving behind embedded minerals to form dark skin-like the grimy crust on an old snowbank. This icy surfaces gets darker with age. More recent impacts dig up cleaner ice and leave bright craters. As you can see on Callisto in figure 18.3, Ganymede has some younger bright groove terrain believed to be the systems of faults in a brittle crust. Some sets of grooves overlap other sets of grooves, suggesting extended episodes of geological activity. So which website do we use if there is cloud cover to check the position of the moon from our location? You can use Stellarium. So I've said this, don't underestimate the moon assignment. So starting now with your observations is cutting it. So that means you don't have any room for error because it has to be in, if I'm correct, the 31st. So you have really led this to the last moment. So don't underestimate it. But if you want to do your, if you're only starting your observations now, the best time would be around about 5 a.m. in the mornings. In image A, the contrast enhanced visual wavelength image of Ganymede shows the frosty poles at the top and bottom, the old dark terrain and a brighter groove terrain. Then in image B, a band of bright terrain on Ganymede runs from left to upper right, and a collapsed area, a possible caldera, lies at the center of this visual wavelength image. Calderas form where subsurface liquid has drained away, and the bright areas contain other features associated with flooding by water. The density of the next moon inward, Europa, is 3 grams per cubic centimeter, which means that Europa is mostly rock with thin icy crust. The visible surface is very clean ice, contains very few craters, has long cracks in the icy crust, and includes complicated terrain that resembles blocks of ice in Earth's Arctic Ocean. The pattern of mountain-like folds on its surface suggests that the icy crust breaks as the moon is flexed by tides. Europa's gravitational influence on the Galileo spacecraft reveals that a liquid water ocean, perhaps 200 kilometers deep, lie below the 10 to 100 kilometer thick crust. The lack of craters tells you that Europa is an active world where craters are quickly erased. In image A, the icy surface of Europa is shown here in natural color. Many folds are visible on its surface, but very few craters. The bright crater Pugel is a young impact feature. In image B, this circular bullseye is the remains of a crater 140 kilometers in diameter. So notice the younger cracks and folds that cross the older impact feature. Image C, like icebergs on the ocean, blocks of crust on Europa appear to have floated apart and rotated. The blue icy surface is stained brown by mineral-rich water venting from below the crust. White areas are ejecta from the impact that form Pugel crater. Image D, the gravitational influence of Europa on the passing Galileo spacecraft shows that this moon has differentiated into a dense core and rocky mantle. Magnetic interactions with Jupiter show that it has liquid water ocean below its icy crust. Heat produced by tidal heating could flow outward as convection in such an ocean and drive geologically activity in the icy crust. Images from spacecraft reveal that Io, the innermost of the 4 Galilean moons, has over 100 volcanic vents on its surface. The active volcanoes throw sulfur-rich gas and ash high above the surface. That ash falls back to bury the surface at a rate of a few millimeters a year. This explains why you see no impact craters on Io. They are covered up as fast as they form. Io's density is 3.6 grams per cubic centimeter, showing that it is composed of rock and metal. Its gravitational influence on the passing Galileo spacecraft reveal that it is differentiated into a large metallic core, a rocky mantle, and a low-density crust. These enhanced color images of volcanic features on Io were produced by combining visual and near-infrared and digitally enhancing the colors. To human eyes, most of Io would look pale yellow and light orange. So that unless I was going through the quiz, we will go through the quiz in the last 10 minutes of the lecture. The activity you see in the Galilean moons must be driven by energy flowing outward. Yet, these objects are too small to have remained hot from the time of their formation. Io's volcanism seems to be driven by tidal heating. Io follows a slightly elliptical orbit caused by its interactions with the other moons. As Io's distance from Jupiter varies, the planet's gravitational field flexes the moon with varying tidal force, and the resulting friction heats Io's interior. That heat following outward causes the volcanism. Europa is not as active as Io, but it also must have heat source, presumably tidal heating. Ganymede is no longer active, but when it was younger, it must have had internal heat to break the crust and produce the grooved terrain. So to go through the scope needs to know, I'm also going to give you the scope at the end of this lecture. In fact, those three moons are linked together in orbital resonances. Io orbits Jupiter 4 times, while Europa orbits twice and Ganymede orbits once. These resonances keep all three orbits slightly elliptical and drive tidal heating that makes the moons active now, or made them active in the past. Distant Callisto is not caught in this orbital resonance and appears never to have been strongly active. Given the lack of surface activity, it is surprising that there is evidence of a subsurface ocean within Callisto as well as in Europa and Ganymede. Astronomers have known for centuries that Saturn has rings, but Jupiter's rings was not discovered until 1979, when the Voyager 1 spacecraft sent back photos. Less than 1% as bright as Saturn's icy rings. Jupiter's rings are very dark and reddish, showing the material is rocky rather than icy. So this is a bit off topic, but do you guys know anything about Voyager spacecraft? Mr. Melville, what is the correct pronunciation? The Voyager 1 and Voyager 2 spacecraft are already in deep space. They are in the Oort cloud and are the... thank you, Mr. Melville. And so the Voyager spacecraft are the furthest man-made objects from Earth. So I'm not exactly sure how far they are, but you can Google it. I know at some point in the next couple of years, we will lose communication with Voyager 1. It's past the edge of the solar system. They are in the Oort cloud. So yes, in a couple of years, we will lose contact with Voyager 1 because then we need more power on its transmitters and bigger antennas, so it becomes more difficult to pick up signals from the Voyager spacecraft. But yes, they still have power, still operating, and still moving deeper and deeper into space. So what is the point of a spacecraft that we can't communicate with? So that is a very good question. So remember, if we want to communicate with something in deep space, you need a powerful transmitter to be able to send signals. And then you need a powerful receiver to be able to pick up those signals. So here on Earth, we can build better and better and better receivers, and we can also build better transmitters to send information to Voyager. But the problem is Voyager's transmitter is not that powerful, and we cannot upgrade Voyager's transmitter. So it comes back to the 1/r² rule. So the further the object is away, the more difficult it is to detect. And at some point, even with our best radio telescopes and best receivers, we won't be able to pick up Voyager anymore. Astronomers can also conclude that the ring particles are mostly microscopic. Photos of the ring show that it is very bright when illuminated from behind. Called forward scattering. Large particles do not scatter light forward. The ring filled with basketball-sized particles would look dark when illuminated from behind. Forward scattering tells you that Jupiter's rings are made of tiny grains with diameters approximately equal to the wavelengths of light, less than a millionth of a meter, about the size of particles in cigarette smoke. So question, so sir, since they are so far, is physical maintenance not possible for them? Yes, physical maintenance is not possible because how can we, so that means we would need to send another spacecraft to do physical maintenance on Voyager. So if I'm correct, Voyager has been launched in 1970 or 1980, around about there. So say it's almost, say, 40 years back when it was launched. So if we need to do maintenance on it, we need to have a spacecraft that is moving faster than Voyager to catch it, and it will take, say, if moving faster, somewhere from 40 to 60 years to catch up with it. So yes, physical maintenance is therefore impossible. So something interesting, so we are careful of what we launched into space, but something interesting, the Voyager spacecraft contains a engraved metal plate on it that shows who we are as humans and how to get to Earth. So it's a roadmap of who we are and where we are that's left on the Voyager spacecraft for in case a other civilization picks it up in the future. In image A, the main ring of Jupiter, illuminated from behind, glows brightly in this visual image made by the Galileo spacecraft. What it was within Jupiter's shadow. Image B, digital enhancement and false color reveal the halo of ring particles that extends above and below the main ring. The halo is just visible in the panel. Image C, structure in the ring is probably caused by the gravitational influence of Jupiter's inner moon. The rings orbit inside the Roche limit. So remember, we have talked about Roche limits and Roche lobes in a previous lecture. The distance from a planet within which a moon cannot hold itself together by its own gravity. If a moon were to come inside the Roche limit, tidal forces would overcome the moon's gravity and pull the moon apart. So you guys understand what I meant, or what I was trying to say with the gravitational forces and tidal forces. So with this, such as the Earth and the Moon has tidal forces on each other, so does Jupiter have tidal forces with its moons, and the moons have tidal forces on Jupiter, but the different moons also has tidal forces with each other as well. So the Roche limit is about 2.4 times the planet's radius, depending somewhat on the relative densities of the planet and the orbiting material. The rings of Saturn, Uranus, and Neptune also lie inside the respective Roche limits for each planet. Now you can understand Jupiter's dusty rings. If a dust speck gets knocked loose from a larger rock inside a Roche limit, the rock's gravity cannot hold the dust speck. For that same reason, the billions of dust specks in the rings can't pull themselves together to make a moon because of tidal forces inside the Roche limit. Thinking about a plate in a sense, we could make the analogy that we have given strangers over the internet directions to our house. Yes, I watch myself, I say, yes, that is true. And also think about it, and that we're going to discuss all these topics in our upcoming lecture. But we have been broadcasting radio waves since we discovered and invented radio, television. So we've been almost now for 100 years been broadcasting electromagnetic radiation away from Earth. And that's another way a civilization can know where Earth is and find us. You can be sure that Jupiter's ring particles are not old. The pressure of sunlight and the planet's powerful magnetic field can quickly alter the orbits of the particles. Images show faint ring material extending down towards the cloud tops. Evidently, dust specks spiraling toward Jupiter. Dust is also lost from the ring as electromagnetic effects force it out of the central plane to form density halo above and below the ring. Another reason the ring particles can't be old is that the intense radiation around Jupiter tends to grind the particles down to nothing in a century or so. Therefore, the ring you see today can't be material left over in its current situation since the formation of Jupiter. Instead, the ring must be continuously resupplied with new dust. Observations made by the Galileo spacecraft provide evidence that the source of the ring material is meteorites eroding the small moons Andraste, Metis, Amalthea, and Phoebe that orbit near or within the rings. So yes, you are correct, Mr. Pretorius. So yes, the Roche limits on the planet must be quite spectacular. The rings around Saturn, Uranus, and Neptune are also known to be short-lived. So they also must be resupplied by new material, probably eroded from nearby moons. Aside from supplying the Jovian planets rings with particles, moons also act to confine the rings, keep them from spreading outward, and alter their shapes. You will explore these processes in detail when you study the rings of the other planets later in this chapter. So, legend just said, I might disconnect suddenly. That's no problem at all. So, I understand load shedding problem. We've put all the evidence together and tell the story of Jupiter. Creating such a logical argument of evidence and hypothesis is the ultimate goal of planetary astronomy. Jupiter formed far enough from the Sun to incorporate large numbers of icy planetesimals, but must have grown rapidly. Once it was about 15 times more massive than Earth, it could grow by gravitational collapse, capturing gas directly from a solar nebula. Thus, it grew rich in hydrogen and helium from a solar nebula. Its present composition resembles the composition of the Sun and the solar nebula. Jupiter's gravity is strong enough to hold onto all its gases, even hydrogen. The large family of moons may be mostly captured asteroids, and Jupiter may still encounter wandering asteroid or comet now and then. So this is interesting. So Jupiter is actually a shield against asteroids and comets for Earth and other planets. Because Jupiter is the largest planet in the solar system, it also is the planet with the largest gravitational field. So it captures most asteroids and comets, and it's actually protecting Earth. And something that you'll see or hear some planetary scientists call Jupiter a failed star because its composition is a lot like the Sun's, but it stopped and it doesn't continue with fusion reaction or can't fuse elements together. So that's one of the reasons it is called a failed star. But some other people make a joke and say Jupiter is an overachieving planet. So some of these are deflected, and some, like comet Schumacher-Levy 9, that struck Jupiter in 1994, actually fall into the planet. Dust blasted off the inner moons by a meteorite impact settles into the equatorial plane from Jupiter's ring. No problem, I completely understand load shedding. The 4 Galilean moons are large and seem to have formed like a mini solar system in a disk of gas and dust around the forming planet. The innermost Galilean moon, Io, is densest, and the densities of the other decrease as you move away from Jupiter, similar to the way the densities of the planets decrease with distance from the Sun. Perhaps the inner moons incorporated less ice because they formed close to the heat of the glowing planet. You can recognize that tidal heating also has been important. An intense heating of the inner moons could have driven off much of their ices. This, a combination of two processes, may be responsible for the composition of the Galilean moons. Saturn is most famous, so before continuing to Saturn, what can you tell me about the Juno probe that visited Jupiter? So, don't you, astronomers also has a bit of sense of humor, so all Jupiter's moons is named after his lovers, and Juno is Jupiter's wife. So they literally send Jupiter's wife to go check up on Jupiter. And yes, Juno is still working. Saturn is most famous for its beautiful rings, easily visible through the telescopes of modern amateur astronomers. Large Earth-based telescopes have explored the planet for many decades. The first close-up views came in when Voyager probes flew past Saturn in 1980 and 1981. The Cassini spacecraft went into orbit around Saturn in 2004 and began an extended exploration of the planet, its rings, and its moons. Yes, Juno is still sending back data. So if I'm correct, you are correct, Mr. Swanepoel, but I'm not exactly sure what happened there. So as you can see in figure 18.1, Saturn shows a faint belt zone circulation, but Voyager, Cassini, and Hubble Space Telescopes images confirm that belts and zones are present, and that the associated winds are up to 3 times faster than the winds on Jupiter. Belts and zones on Saturn are less visible than on Jupiter because they occur deeper in Saturn's colder atmosphere, below a layer of methane haze. Image A, Saturn's belt zone circulation is not very distinct at visible wavelengths. These images were recorded when Saturn's southern hemisphere was tipped towards Earth, in image B. Because Saturn is colder than Jupiter, the clouds form deeper in a hazy atmosphere. Notice that the 3 cloud layers on Saturn form at about the same respective temperatures as the 3 cloud layers on Jupiter. So here we can see we have ammonia, ammonium hydrosulfide, and water. Saturn is less dense than water, so in theory, Saturn would be able to float on water. Suggesting like it is, like Jupiter, rich in hydrogen and helium. Saturn is the most oblate of the planets, and this is evidence that its interior is mostly liquid with only a small core of heavy elements. Because its internal pressure is lower, Saturn has less liquid metallic hydrogen than Jupiter. Perhaps that is why Saturn's magnetic field is 20 times weaker than Jupiter's. Like Jupiter, Saturn radiates more energy than it receives from the Sun, and models predict that it too has a very hot interior. Saturn has nearly 50 known moons. Saturn has nearly 50 known moons, many of which are small, and all of which contain mixtures of ice and rock. Many are probably captured objects. So planet floating on water, astronomers are funny sometimes. That you can say again. The largest of Saturn's moons is Titan, a bit larger than the planet Mercury. Measurements of the effect of its gravitational field on probes passing nearby indicate that it has a rocky core under a thick mantle of ices. Titan is so cold that its gas molecules do not travel fast enough to escape. It has an atmosphere composed mostly of nitrogen, with traces of argon and methane. The ultraviolet component of sunlight converts some of the methane into complex carbon-rich molecules that collect into small particles, filling the atmosphere with orange smog. Some of those particles evidently settle downward and coat parts of the surface with what has been described as organic goo, meaning it is composed of carbon-rich molecules and is probably semi-liquid. So, are Saturn and Jupiter going to shrink a bit when they reach thermal equilibrium? If so, how much they will shrink. So yes, I believe they will shrink as the temperature changes, but I'm not sure with how much exactly. As the Huygens probe descended through Titan's smoggy atmosphere is in image A, then image B, it photographed the surface from an altitude of 8 kilometers. Although no liquid was present, dark drainage channels led into the lowlands. In an image C, once the probe landed on its surface, it radioed back photos showing a level of plain and chunks of ice smoothed by moving liquid. Radar images from the Cassini orbiter revealed lakes of liquid methane and ethane around the poles. The Cassini spacecraft dropped the Huygens probe in the atmosphere of Titan. Huygens found, as expected, that Titan's surface is composed mainly of ices, of water and methane, at 2180 degrees Celsius. Images made by the descending probe showed dark drainage channels suggesting that liquid methane falls as rain, washes the dark goo off the higher terrain, and drains into lowlands. Such methane downpours may be rare. However, no direct evidence of liquid methane was detected as the probe descended, but later radar images made by the Cassini orbiter have detected what appear to be lakes, presumably containing liquid methane. Infrared images suggest that the presence of methane volcanoes that replenish the methane in the atmosphere, so Titan must have some internal heat source to power the activity. Most of the remaining moons of Saturn are small and icy, have no atmospheres, are heavily cratered, and have dark, ancient surfaces. The moon in Clydeus, however, shows signs of recent geological activity. Some parts of the surface contain 1,000 times fewer craters than other regions. An infrared observation showed that its south polar region is usually warm and venting water and ice containing organic compounds. Evidently, a reservoir of liquid water lies just below the surface. At some point in its history, the moon may have been caught in a resonance with another moon and had its interior warmed by tidal heating. In the right image, the bright, clean, icy surface of Enceladus does not look cold. Some areas have few craters and numerous cracks and lanes of grooved terrain resemble the surface of Jupiter's moon Ganymede. Enceladus is venting water, ice, and organic molecules from geysers near its south pole. The thermal infrared image reveals internal heat leaking to space from the tiger stripe cracks where the geysers are located. Like nearly all moons in the solar system, Saturn's moons are tidally locked to the planet, rotating to keep the same side facing the planet. The leading side of these moons, the side facing forward in the orbit, is sometimes modified by debris. Lepidus, for example, has a crater trailing side about as bright as dirty snow. But its leading side is as dark as fresh asphalt. One hypothesis is that the dark material is carbon-rich dust from meteoroid impacts on Phoebe, the next moon outward from Saturn. Lepidus also has a strange equatorial ridge that may have been produced by rapid rotation when the moon was young. The rings of Saturn are perhaps the most beautiful sight in our solar system. Notice 3 important ideas plus 1 new term. The rings are made up of billions of ice particles, each in its own orbit around the planet. The ring particles you observe now can't be as old as Saturn. The rings must be replenished by impacts on Saturn's icy moons or other processes. The same is true if the rings around the other Jovian planets. Secondly, The gravitational effects of small moons are called shepherd satellites, can confine some rings in narrow strands or keep the edges of the ring sharp. Moons can also produce waves in the rings that are visible as tightly wound ringlets. And lastly, the ring particles are confined in a thin plane spread among small moons and confined by gravitational interactions with larger moons. The rings of Saturn and the rings of the other Jovian worlds are created by and controlled by each planet's moons. Without the moons, there would be no rings. Observations made by the Cassini spacecraft shows that the ring particles have compositions that resemble that of Saturn's distant icy moon Phoebe. A large impact on Phoebe may be part of the complex history of Saturn's rings. Tiny icy particles from geysers from the moon Enceladus are understood to be the main source of material for the outermost low-density ring, discovered by the Cassini probe and named the E ring, within which Enceladus orbits. Saturn formed in an outer solar nebula, where ice particles were stable and may have contained more trapped gases. The protoplanet grew rapidly and became massive enough to attract hydrogen and helium by gravitational collapse. The heavier elements sank to the middle to form a small core, and hydrogen formed a liquid mantle containing liquid metallic hydrogen. The outward flow of heat from the interior drives convection inside a planet that helps produce its magnetic field. Because Saturn is smaller than Jupiter, the internal pressure is less. The planet contains less liquid metallic hydrogen and its magnetic field is weaker. The rings can't be primordial. That is, they can't be material left over from the formation of the planet. Such ices would have been vaporized and driven away by the heat of the protoplanet. Rather, you can suppose that the rings are debris from the occasional impacts of meteoroids, asteroids, comets on Saturn's icy moons. Some of Saturn's moons are probably captured asteroids that wandered too close, but larger moons almost certainly formed with Saturn. Many of Saturn's moons have ancient surfaces, but Enceladus and Titan have fresh surfaces, evidently ongoing geological activity. You will see a few more examples of recent geologic activity and also of captured moons when you explore further from the Sun. Now that you are familiar with the liquid giants in our solar system, you will be able to appreciate how strange the ice giants Uranus and Neptune are. Uranus especially seems to be the oddball of the family. Uranus is only 1/3 the diameter of Jupiter and only 1/20th as massive. 4 times further from the Sun than Jupiter, its atmosphere is almost 100 degrees colder than Jupiter's. Uranus never grew massive enough to capture large amounts of gas from a nebula as Jupiter and Saturn did, so it has much less hydrogen and helium. Its internal pressure is enough less than Jupiter's that it should not contain any liquid metallic hydrogen. Models of Uranus, based in part of its density and oblateness, suggests that it has a small core of heavy elements and a deep mantle of partly solid water. Although that material is referred to as ice, it would not be anything like ice on Earth. At the temperatures and pressures inside Uranus, the mantle also probably contains rocky material plus dissolved ammonia and methane. Circulation in that electrically conducting mantle may generate the planet's peculiar magnetic field, which is highly inclined to its axis of rotation. Above the mantle lies a deep hydrogen and helium atmosphere. Uranus rotates on its side, with its equator inclined about 98 degrees to its orbit. As a result, the winter-summer contrast is extreme, with the Sun passing near each of the planet's celestial poles at a solstice. So half of the planet is in perpetual darkness and the other half in perpetual light for the 21-year-long summer and winter seasons. Compare that with seasons on Earth. Discussed in Chapter 3, Section 1, when Voyager 2 flew past in 1986, the planet's south pole was pointed almost directly at the Sun. So imagine living on a planet that is basically 21 years summer, 21 years winter, and also 21 years night, 21 years day. Uranus rotates on an axis that is tipped about 98 degrees from the perpendicular to its orbit. So its seasons are extreme. When one of its poles is pointed nearly at the Sun, a solstice, and inhabitants of Uranus would see the Sun near celestial pole, never rising or setting. As Uranus orbits the Sun, the planet maintains the direction of its axis in space, and thus the Sun moves from pole to pole. At a time of an equinox on Uranus, the Sun would be on a celestial equator and would rise and set with each rotation of the planet. Compare with similar diagrams for Earth on the right-hand page of Concept Art 3A. That can be true, Mr. Swanepoel. Voyager 2 photos show a nearly featureless ball. The atmosphere is mostly hydrogen and helium, but traces of methane absorb red light and this make the atmosphere look green-blue. There is no belt zone circulation visible in the Voyager photographs, although computer enhancements revealed a few clouds and bands around the South Pole. In the decades since Voyager 2 flew past Uranus, spring has come to the northern hemisphere of Uranus and autumn to the southern hemisphere. Images made by the Hubble Space Telescope and new large Earth-based telescopes reveal changing clouds and cloud bands in both hemispheres. In image A, if you had been riding on board Voyager as it passes Uranus, the planet would have looked like a bland green ball. Image B, later ground-based contrast-enhanced images reveal traces of belt zone circulation deep in the atmosphere. So here we can see Uranus also has rings, and no clouds were visible in the Voyager 2 flyby. Until recently, astronomers could see only 5 moons orbiting Uranus. Voyager 2 discovered 10 more small moons in 1986, and more have been found in images recorded by powerful telescopes on Earth. The International Astronomical Union, which decides definitions and naming conventions for celestial objects and surface features, has specified that moons of Uranus will continue to be named after characters in place of William Shakespeare and Alexander Pope. So this is something interesting about Uranus. While all the other naming conventions in the solar system is Greek and Roman mythology, Uranus moons are named after the plays and characters of Shakespeare and Alexander Pope. The 5 major moons of Uranus are smaller than Earth's moon and have all dark cratered surfaces. A few have deep cracks, produced perhaps when the interior froze and expanded. In some cases, liquid water lava appears to have erupted and smoothed regions. Ariel is marked by broad, smooth floored valleys that may have been cut by flowing ice. Evidence of geological activity on the 2 Uranian moons. A. Ariel has an old cratered surface, but some regions are marked by broad, shallow valleys with few craters. And B. The face of Miranda is marked by ovoids, which are believed to have formed when internal heating caused slow convection in the ice of Moon's mantle. Note that a 5-kilometer high cliff at the lower edge of the Moon. Miranda, the innermost moon, is only 14% diameter of Earth's moon, but its surface is marked by grooves called ovoids. They may have been caused by internal heat driving convection in the icy mantle. Rising currents of ice have deformed the crust and created ovoids. By counting craters on the ovoids, astronomers conclude that the entire surface is old and the moon is no longer active. Perhaps it was warmed by tidal heating long ago. The rings of Uranus are not easily visible from Earth. The first hint that Uranus has rings comes from occultations, the passing of the planet in front of a star during which the rings momentarily block the star's light. Observed by astronomers on board the Kuiper Airborne Observatory in 1977. Most of what astronomers know about these rings comes from observations by the Voyager 2 spacecraft. Their composition appears to be water ice mixed with methane that has been darkened by exposure to solar wind particles trapped in the planet's magnetosphere. Notice 3 important points plus 1 new term. The rings of Uranus were discovered during an occultation when Uranus crossed in front of a star. Secondly, the rings are dark, contain little dust, and are confined by small moons. Thirdly, particles orbiting in the rings around Uranus and Neptune cannot survive for long periods. So the rings need to be resupplied with material from impacts on moons, as is also true for the rings around Jupiter and Saturn. When you read about Neptune's rings late in this chapter, you can return to this art spread and see how closely the two ring systems compare. In 2006, astronomers found 2 new very faint rings orbiting far outside the previous land rings of Uranus. The newly discovered satellite map appears to be the source of particles of the larger ring, and the smaller of the new rings is confined between the orbits of the moons Portia and Rosalind. Now, I know some of this stuff can be a bit weird and funny. Uranus never grew massive enough to capture large amounts of gas from a solar nebula as did Jupiter and Saturn. Uranus is rich in water and ice rather than in hydrogen and helium. Modern models of the origin of the solar system suggest that Uranus and Neptune formed closer to the Sun than their present positions. Interactions with massive Jupiter and Saturn could have gradually moved Uranus and Neptune outward, and tidal effects may have produced Uranus' peculiar rotation. Another hypothesis is that Uranus was struck by a large planetesimal as it was forming and given its highly inclined rotation. The highly inclined magnetic field of Uranus may be produced by convection in its electrically conducting mantle. With very little heat flowing out of the interior, this convection must be limited. Now we are touching Neptune. Through a telescope on Earth, Neptune looks like a tiny blue dot with no visible cloud features. In 1989, Voyager 2 flew past and revealed most of what we know today about Neptune. So the International Astronomical Union really has fun with the naming of these celestial objects. Yes, they do. Almost exactly the same size as Uranus, Neptune has a similar interior. Model calculations predict that a small core of heavy elements lies within a slushy mantle or water ices, and rocky materials below a hydrogen-rich atmosphere. Yet Neptune looks quite different on the outside of Uranus. Neptune is dramatically blue and has active cloud formations. Neptune's dark blue tint is caused by its atmospheric composition of 1.5 times more methane than Uranus. Methane absorbs red photons better than blue and scatters blue photons better than red, giving Neptune a blue color and Uranus a green-blue color. Something interesting that you guys know that Neptune wasn't discovered through a telescope. Neptune was mathematically determined. So when you look at the rest of the solar system and start studying the gravitational influence of all the bodies in the solar system, they realized in the area where Neptune was, because Neptune is not visible with the naked eye, only through a telescope, Something must be a certain body of a certain size to have a gravitational influence. So they calculated where that is. Then, when they pointed the telescope to that point, there was Neptune. And Mr. Mabel, that's why Planet 9 is not discovered. So, if you want to do the same principle, then you can calculate to extreme accuracy where Planet 9 should be, but if you point your telescope towards it, there's nothing. So Planet 9 does not exist. Atmospheric circulation on Neptune is much more dramatic than on Uranus. When Voyager 2 flew by Neptune in 1989, the largest feature was the Great Dark Spot, roughly the size of Earth. The spot seemed to be an atmospheric circulation pattern, much like Jupiter's Great Red Spot. Smaller spots were visible in Neptune's atmosphere, and photons showed they were circulating like hurricanes. More recently, the Hubble Space Telescope has photographed Neptune and found the Great Dark Spot is gone, and new cloud formations have appeared, as shown in figure 18.14. Evidently, weather patterns on Neptune are very changeable. In image A, because Neptune's equator is inclined in 28 degrees in its orbit, it experiences seasons. The planet's orbital period of 165 years causes each season to last more than 40 years. In image B, since Voyager 2 visited in 1989, spring has come to the southern hemisphere and the weather has changed significantly. That is surprising because sunlight on Neptune is 900 times dimmer than on Earth. The atmospheric activity on Neptune is apparently driven by heat flowing from the interior plus some contribution by dim sunlight 30 AUs from the sun. The heat causes convection in the atmosphere, where the rapid rotation of the planet converts into high-speed winds, eye-level white clouds of methane ice crystals, and rotating storms visible as spots. Neptune may have more activity than Uranus because it has more heat flowing out of its interior for reasons that are unclear. Like Uranus, Neptune has a highly inclined magnetic field that must be linked to circulation in the interior. In both cases, astronomers suspect that ammonia dissolved in the liquid water mantle makes the mantle a good electrical conductor, and that convection in the water, coupled with the rotation of the planet, drives dynamo and generates the magnetic field. Neptune has two moons that were discovered from Earth before Voyager 2 flew past in 1989. Voyager discovered 6 more very small moons. Since then, a few more small moons have been found by astronomers using Earth-based telescopes. The 2 largest moons have peculiar orbits. Nereid, about a tenth the size of Earth's moons, follows a large elliptical orbit, taking nearly an Earth year to circle Neptune once. Triton, almost 80% of the size of Earth's moon, orbits Neptune retrograde, so that means backwards. These odd orbits suggest that a system was disturbed long ago in an interaction with some other body, such as a massive planetesimal. With a surface temperature of about 36 Kelvin, so this in Fahrenheit is wrong. Looks like when I copy and pasted this temperature, the format screwed us up, but yes, it's 36 Kelvin. Triton has an atmosphere of nitrogen and methane about 10 to the power 5 times less dense than Earth's. A significant part of Triton is ice. And deposits of nitrogen frost are visible at the southern pole, which at the time Voyager 2 flew past had been turned towards sunlight for 30 years. The nitrogen frost appears to be vaporizing in the sunlight and is probably refreezing in the darkness at Triton's north pole. Visible wavelength images of Neptune's moon's Triton. Image A. Triton's southern polar cap is formed of nitrogen frost. No dark smudges caused by organic compounds sprayed from hydrogen geysers, an absence of craters. Image B. These round basins on Triton appear to have been repeatedly flooded by liquid from the interior. Many features on Triton suggest it has had an active past. It has few craters on its surface, but it does not have long faults that appear to have formed when the icy crust broke. Some approximately round basins, about 400 kilometers in diameter, appear to have been flooded time after time by liquids from the interior. Analysis of dark smudges visible in the southern polar cap reveals that these are deposits produced when liquid hydrogen in the crust, warmed by the sun, erupts from vents and spews up to 8 kilometers in high into the atmosphere. Methane in the gas is covered by solar ultraviolet radiation into dark compounds that fall back, leaving black smudges. By counting craters on Triton, planetary scientists conclude that the surface has been active as recently as 1 million years ago and may still be active. The energy source for Triton's geyser activity could come from radioactive decay. The moon is 2/3 rock, and although such small world would not be able to generate sufficient radioactive decay to keep molten rock flowing to its surface, future Triton may be the site of water-ammonia volcanism. A mixture of water and ammonia could melt at very low temperatures and erupt to resurface parts of the moon. I'm just waiting for the slide to load on my side. Neptune's rings are faint and very hard to detect from Earth, but they illustrate some interesting principles of comparative planetology. Comparing the rings of Neptune with those on Uranus, notice 2 additional points. Neptune's rings, named after the astronomers involved in the discovery of the planet, are similar to those of Uranus but contain more small dust particles. Also, Neptune's rings show another way that moons can interact with rings. One of Neptune's moons is producing short arcs in the outermost ring. Neptune's rings resemble the rings of Uranus, Saturn, and Jupiter in one important way. As you have already learned, these rings can't be primordial. That is, they can't have lasted since the formation of the planets. Planetary rings are constantly being made. So yes, Mr. Pretorius, but as you will learn in the last chapter, there are other ways we can look for life, and there's other ways other life can look for us. Neptune must have formed much as Uranus did, growing slowly and never becoming massive enough to trap large amounts of hydrogen and helium. It developed a core of heavy elements, a mantle of slushy ices and rock, and a deep hydrogen-rich atmosphere. Neptune's internal heat may be generated partly by radioactive decay in its core and partly by dense material sinking inward. Laboratory experiments show that at the temperatures and pressures expected deep in the atmospheres of Neptune and Uranus, methane can decompose and the released carbon might form diamond crystals, perhaps as large as pebbles. The continuous flow of diamonds falling into the planet's interior would release gravitational energy and help warm the planet. This process may be the source of some of Neptune's internal heat. But the lack of internal heat in Uranus remains a puzzle. The possibility of a planet-wide hailstorm of diamonds serves to remind you that other worlds are truly unearthly and may harbor things you can hardly imagine. The heat flowing outward towards Neptune's surface can drive convection, produce a magnetic field, and help create atmospheric circulation. The moons of Neptune suggest some cataclysmic encounter long ago put Nereid into a long period elliptical orbit, and Triton into a retrograde orbit. You have seen evidence of major impacts throughout the solar system, so such interactions may have been fairly common. Certainly, impacts on the satellites could provide the debris that is trapped among the smaller moons to form rings. Out on the edge of the solar system orbits a family of small icy worlds. Pluto was the first to be discovered in 1930, but modern telescopes have found more. You may have learned in school that there are 9 planets in our solar system, but in 2006, the IAU voted to remove Pluto from the list of planets and reclassify it as a dwarf planet. Pluto is a very small icy world. It isn't Jovian and it isn't terrestrial. Its orbit is highly inclined and elliptical, enough that Pluto actually comes closer to the Sun than Neptune at times. To understand Pluto's status, you can use comparative planetology to analyze Pluto and then compare it with its neighbors. So, according to me, Pluto should have been kept a planet just to keep tradition alive and for tradition's sake, but the IAU has voted and that's where we is. But I see someone's going to try to bring it up again to have it reintroduced as a planet due to just tradition, but we'll see what will happen on that. So Pluto is very difficult to observe from Earth as its diameter is 2,370 kilometers, smaller than Australia and only 2/3 the diameter of Earth's moon. In Earth-based telescopes, Pluto never looks like more than a faint point of light. And even in Hubble Space Telescope images, it shows little detail. Orbiting so far from the Sun, Pluto is cold enough to freeze most compounds you think of as gases, and spectroscopic observations have found evidence of nitrogen and methane ices on its surface. Pluto has a thin atmosphere of nitrogen and carbon monoxide with small amounts of methane. Pluto has 5 known moons. 4 are quite small, but Charon is relatively large, with half of Pluto's diameter. Charon orbits Pluto in an orbit inclined at 180 degrees to the plane of Pluto's orbit around the Sun, which means Charon's motion is retrograde. Pluto and Charon are tidally locked facing each other, so Pluto's axis of rotation is inclined at the same large angle to its orbit, such that its rotation is also retrograde. Knowing Charon's orbital period of 6.4 days and orbiting major axis of 19,600 kilometers, allow to use Kepler's third law to calculate that the total mass of the system is about 0.0024 Earth masses. Most of that mass is Pluto, which has about 9 times the mass of Charon. Known diameters and masses of Pluto and Charon allows determination that the densities are respectively 1.9 and 1.7 grams per cubic centimeter. That indicates that both Pluto and Charon must contain about 30 to 40% ice and 60 to 70% rock. The New Horizons spacecraft flew past Pluto in July 2015, radioing back impressive images and other measurements. Close-up pictures show mountains up to 3.5 kilometers high. Methane and hydrogen ice would not be strong enough to stand that tall, so planetary scientists conclude that the mountains must be made of water ice that would be rock hard at Pluto's temperature. The lack of craters on and near those mountains indicates that this particular landscape is very young, say no older than 100 million years. One of the youngest surfaces observed in the solar system. Pluto has been active geologically recently, which means that the heat must be flowing outward. Although planetary scientists wonder what the internal heat source could be. Charon's orbit is perfectly circular, so tidal heating is not the explanation. Radioactive decay would seem to be the only plausible alternative, although that heat source should also have faded long ago. One planetary scientist on New Horizons team remarked, "This may cause us to rethink what powers geological activity on many other icy worlds. Pluto turns out to be a world full of surprises." So what defines a planet? To understand why Pluto is no longer considered a planet, you should recall what you have already learned about the Kuiper Belt. Since 1992, astronomers have discovered more than 1,000 icy bodies orbiting beyond Neptune. There may be as many as 100 million Kuiper Belt objects larger than 1 kilometer in diameter. They are understood to be icy planetesimals left over from the outer solar nebula. Some of the Kuiper Belt objects are quite large, and one, Eris, is about the same diameter as Pluto, but is 27% more massive. Three other Kuiper Belt objects found so far, Sedna, Quaoar, and Orcus, are half the size of Pluto or larger. Eris, Quaoar, and Orcus are known to have moons of their own. In that way, they resemble Pluto and its family of moons. A bit of comparative planetology shows that Pluto is not related to Jovian or terrestrial planets. It is obviously a member of a newfound family of worlds that orbit beyond Neptune. These bodies must have formed at about the same time as the 8 classical planets of the solar system, but they did not grow massive enough to clear their orbital zones of remnant planetesimals and consequently remain embedded among the swarm of other objects in the Kuiper Belt. The IAU criteria for a full planet status is that the object must be large enough that its gravity has pulled it into a spherical shape, and also large enough to dominate and gravitationally clear its orbital region of most or all other objects over a span of billions of years. Eris and Pluto, the largest objects found in the Kuiper Belt, and Ceres, the largest object in the asteroid belt, are too small to clear the orbital zones of other objects and therefore do not meet the standard for being called planets. On the other hand, all three are large enough to be spherical, so they are the prototypes of a new class of object defined by the IAU as dwarf planets. So Pluto and the Plutinos. So no, the section is not about the 1950s rock band. It is about the history of the outer solar system, and it will take you back 4.6 billion years to watch the planets form. More than 100 of the Kuiper Belt objects are caught with Pluto in a 3-to-2 resonance with Neptune. That is, they orbit the Sun twice while Neptune orbits 3 times. The subset of KBOs have been named Plutinos. The Plutinos formed in the outer solar nebula. But how did they get caught in a resonance with Neptune? As you learned earlier, some models of the formation of the planet suggest that Uranus and Neptune may have migrated outward early in the solar system's history. As Neptune moved further from the Sun, its orbital resonance could have swept up small objects like a kind of planetary snowplow. The Plutinos are caught in a 3-to-2 resonance, and other Kuiper Belt objects caught in other resonances. The evidence appeared to support those models that predict that Uranus and Neptune migrated outward. The migration of the outer planets would have dramatically upset the motion of some of the Kuiper Belt objects, and some could have been thrown inward where they could interact with the Jovian planets. Some of those objects may have been captured as moons, and astronomers wonder if moons such as Neptune's Triton could have started life as a Kuiper Belt object. Other objects may have had bodies in the inner solar system and caused the late heavy bombardment episode especially evident on the surface of Earth's moon. The small frozen worlds on the fringes of the solar system may hold clues to the formation of the planets 4.6 billion years ago in the subsequent history of Earth. So, ladies and gentlemen, this was our lecture on the solar system. So now we have finished the solar system. Do you guys guess what remains? So yes, one of the lectures we still need to do is astrobiology. And the other one we still need to do is comets and asteroids. So we will finish up these last two lectures next week, but for now, let's quickly go through the memo of the second quiz. So let me just find my side and open it up. So I will give that right after we go through the memo. Can everyone see my screen? Yes, you can calculate the diameter of the moon through your estimated angular diameter. So the first question is, if it takes light 8 minutes to reach Earth from the Sun and 1.3 hours to reach Saturn, what is the distance from the Sun to Saturn? Do I have any volunteers that can perhaps explain this? Any volunteers? How did you calculate this answer? So yes, you convert 1.3 hours to minutes. We know light here is way too big, and we know that is from the Earth to the Sun is 1 AU. Does 9.7 is the only logical answer. Yes, you can answer it that way, but you know it takes 8 minutes for light to reach the Sun, and the Sun to Earth is 1 AU. 1 AU is 150 million kilometers. So you take that 150 million kilometers, divide by 8, then you know how far light travels in 1 minute. Then you take those 1.3 hours, convert that to minutes, and then you know how far light travels in 1 minute, and you know how many minutes there are, and then voila, you calculate how far it is away, and that is 9.75 AU. Then, secondly, to determine the radius of a distant star, we need to know its temperature and luminosity. So, those are two important concepts throughout this module. If you know what the object's temperature and luminosity is, you can determine the radius. In question 3, absorption lines due to the interstellar medium indicate that some components of the interstellar medium are cold and of low density because the lines are extremely narrow. So remember Kirchhoff's laws. Then question number 4, the first quarter moon rises at about noon. I can zoom in on my side, but you should be able to zoom in and on your side. So if you've done your moon research and worked on your assignment, you will realize first quarter moon always rises at about noon. Then the last question, what is the approximate age of a star cluster if turn-off point lies with spectral type G stars? So now you have to learn and use your HR diagram. So in the HR diagram, we know the turn-off point of the spectral G-type stars are about 10 million years old. So that means the approximate age of that cluster will be 10 billion years old. Is everyone happy with these explanations? Okay, then coming to the semester test. So the semester test, the scope for the semester, so let me just check on my side. So to make it fair for you guys, the scope of the test will be half of the module's work. So the scope will be chapter 1 to 10. So chapter 1 is everything from the night sky and the introduction, and you will end off with the deaths of stars. So chapter 1 to 10, is that fair? Okay, cool. And then I will also provide you guys with a mock test for practice for the semester test. I will, what is it, today's Tuesday, I will release that to you by tomorrow. And then, so next week, Monday and Tuesday, we will have our normal lectures. But if it's fine with you guys, I will schedule 2 question and answer sessions. So one for next week, Wednesday, and one for next week, Thursday. It's not compulsory that I will be active and you can ask questions. So what time next week, Wednesday and Thursday will work for you? So on Thursday's class, I will go through the memo of the mock test. So what time next week, Wednesday and Thursday will work for you guys for recap sessions or question and answer sessions? Will 7 to 8 o'clock I will ask on the group, but if I ask you guys what will the evenings work for, say for example 7 to 8 on Wednesday evening next week and 7 to 8 on Thursday evening next week. Okay, I will ask on the WhatsApp group as well. Then those 2 classes aren't compulsory at all. So the idea is that you study, and if you have questions, then we have a question and answer session during those 2 sessions that you can ask questions and we can discuss. So next week, Thursday, when are you writing next week? What time are you writing next week, Thursday? Or when do you end your semester test? 5:30 to 7:30. We can even do on next week, Thursday, we can even do that class from 8 to 9 if you guys are up for it, just to compensate for you guys writing. So it won't be compulsory, but it will be open for questions and answers. So do you have any interest in quantum gravity? Yes, I have a little bit of, don't know much about it, not my field of expertise, but yes, I have a little interest in it. So that's the last admin. So one thing is just remember your moon assignments. That is also due in about 14 days. Please do not underestimate it. Also know I will be taking plagiarism seriously. So if you guys have no further questions, then you are more than welcome to log off. If you're writing tests this week, good luck with preparation for those tests and good luck with the test itself. Then have a wonderful evening and I will see you all next week. So if you guys have no further questions, I am also going to log off. So have a wonderful evening, guys. You are more than welcome to email me. Pleasure. So I'm also going to log off. So have a wonderful evening, everyone.